What's up? Welcome back. I know you're excited to keep learning about some electrochem, so let's get right after it. In this video, I want to talk to you about how to handle non-standard cells. So remember back to our Thermo 2 unit, we learned delta G and everything was standard. We had a little degree sign up there. You know what it is. You're familiar with it by now. But we talked about what it meant to be standard at that point. 1 atmosphere pressure, 25 Celsius for thermo and electrochem. And then one thing that's important that we didn't talk a lot about with gases in pre-P, but it's really important now, the concentration of these solutions in the cell, standard is 1 molar. So in all those calculations we've recently done with calculating cell potential, just taking the reduction potentials and subtracting them, those were standard. And every one of those assumed 1 molar aqueous concentrations in every cell. Well, we know that's not always the case. So when it's not the case, we can't just subtract cathode minus anode with those reduction potentials we pull out of the back of the book. It won't work. We have to rely on something else. So that tool is called the Nernst equation. And you can see a couple of different forms of the Nernst equation on the screen. It looks really complicated, but it's not. You're familiar with the Nernst equation. You're at least familiar with its origins. It comes from our delta G non-standard equation from back in the thermo unit. So in just a moment, I want to derive it here on paper just to make you get comfortable with it. So basically, you see that equation in the middle of your screen right here from thermo 2. All we're going to do is take that equation and we're going to sub in our latest tool that we added in the previous video, the negative Niffy, into each of those spots for delta G, and then we're going to see what happens. So let's flip over to the dot chem and let's derive some Nernst equation. So remember that we've got delta G non-standard. Let's get that focus all fixed up. Delta G not standard equals delta G standard plus RT log of Q. So remember, it's Q because we do this when we don't know if we are at equilibrium or not. And so now into this equation, we're going to plug in negative Niffy for each of my delta G's. This one right here is negative Niffy standard. So just notice that non-standard delta G is we're going to use our non-standard cell potential E, and standard G's, and we're going to use standard E. I don't know what the focus thinks it's doing, but it's been a little annoying. All right, so we still got here plus RT natural log of Q. All right, so now algebraically we're going to go from here to the Nernst equation, and all I'm going to do is I'm going to factor out negative NF from this side of the equation. And so when I do that, that's going to leave me with standard cell potential plus RT. And since there was no NF to take out here, that means it goes down here. And then we keep our natural log of Q. So why did we do that? Well, just to get rid of negative NF for 2 of our terms. And so that will give us the equation you see at the top of the page. Non-standard potential equals standard potential. And now this term is minus RT over NF, natural log of Q. Now most people don't use that form of the Nernst equation because it's a little bulky with the R's and the T's and the Faraday constants and all that. So what they do is they take these constants, 8.314, 298 for temperature, 96,500 for F, and the mathematical conversion from natural log the common log, which I don't remember off the top of my head, but you plug in all those, and that's how you simplify, excuse me, simplify that down to get this more common form of the Nernst equation. People like that one just because you don't have to write as much. So remember here that Q is going to be products over reactants, just like it has been for, well, I guess several months now. For our electrochemical reaction. And since, remember, we don't put solids into our expressions for Q or K, so normally what this is, normally, I don't like dealing in absolutes here, but normally what this means is that your oxidation product typically goes on top and your reduction on bottom. So that's common, but we're not going to hang our hat on that. We're actually going to look at the equation and see what's up with that. All right, we'll put this aside and I'll bring it back out because there's one more piece of content that I want to mention before we leave this. But let's go right now to an example, and let's do a Nernst equation problem, or solve a problem using the Nernst equation. Again, this problem came out of the Brown and LeMay book. If you have one at home, it's problem 61, 20.61. So this is what the problem gave us. It gave us an equation already written. This is what they said use. And then part A says, what is the standard EMF? So at the top of the page, I did a little pre-work. I went to the back in the appendix and pulled out the reduction potentials for both zinc +2 and nickel 2 and wrote the reduction potentials down. So this is not hard. We know how to find a standard cell potential at this point, or standard EMF. I haven't used the words EMF enough in my videos, and I realized that as I was reading this problem. EMF stands for electromotive force. It's basically the same thing as your voltage. When it says find EMF, you're finding your voltage, your potential. So you can learn more about electromotive forces in physics, but for us, it's the same thing as voltage, okay? All right, so cathode minus anode. I can see that nickel is being reduced. So I'm going to take that negative 0.28 volts, and I'm going to subtract from that my negative 0.763. And I did not pre-calculate this, so let me grab the calculator. Negative 0.28 minus negative 0.763. All right, so this is a 0.483 volts. Yes, sig figs say 0.48. So if you want to put 0.48, go for it. All right, so that's standard. Everything here was 1 molar. We had 1 molar nickel 2 nitrate, whatever it was, and 1 molar zinc nitrate, whatever that was. I promise I don't have corona. All right, so let's move on now to part B, where it wants us to calculate the EMF when the nickel concentration and the zinc concentrations are not 1 molar. There's something else. There's something else. So we're going to find E, and we'll use, let's use the easy version of the Nernst equation. So we're going to use standard minus 0.052 volts, that is a volt, over N times common log of Q. So let's get a few of these pieces of information figured out. We'll just come over here. First of all, standard cell potential we just calculated is 0.483 volts. Okay, got that knocked out. N, we may need to go back to the top and look at our equations to find N. Here I can see I added these up. Both of them were 2 electrons, so it canceled. So here N is 2 moles of electrons. And then we need to find Q. All right, so again, looking at our equation right here, The equilibrium expression for this reaction will be the concentration of zinc over the concentration of nickel. We do not put those solids in here. Don't do it. And so subbing in the numbers that we have, nickel concentration is 3 molar and the zinc concentration is 0.1 molar. So in essence, what we're doing here, if we have non-standard conditions, is we're introducing another driving force to this reaction. The original driving force is just the motion of electrons toward the more electronegative electrode or electrode compartment. So it's just an electron gradient, potential gradient. And now the second driving force is the concentration. And so they'll always also want to get those concentrations to be equal. All right, so let's see. Q here is going to equal 0.033, I bet, but it's late at night and I don't trust myself. So 0.033. I think I went to the proper number of sig figs. All right, so that's it. That's all of our information. Let's come back to the Nernst equation now, and let's plug in all of our little joules. 0.483 volts minus 0.052 volts divided by N, which is 2, and then log of 0.0333 . Alright, let's see what we get here. I've always found this to be easier to work from the right side to the left. If you're good at that sort of thing, I'll just kind of talk you through it here if you're not. Log of 0.0333, enter, times 0.052. Alright, I actually should have done negative 0.052, so when I divide here, so we divide by -2. And then I'm just going to add my E standard, 0.483. So I got the new voltage, and this time I will round it to the proper number of sig figs, to be 0.52 volts. So we actually get an uptick in the voltage here by varying the concentrations. So in essence, what we're doing here is we're stimulating the anode to kind of get after it more, to get that concentration up to where the zinc and the nickel concentrations are more closely equal. And that gives us a little bit of an uptick in our voltage. Which brings me to my last point for this video. We can actually apply this concept to something called a concentration cell. So we've been talking about concentrations. We know if the concentration of both of the electrode compartments is the same, then this Q term goes to natural log of 1, okay, which is just 0. So this whole term zeroes out, and that's when our standard potential equals, E. It's just, that's what we were doing at the beginning of this unit last few weeks of practice, cathode minus anode. Okay. Now, sometimes we can actually make cells out of the same electrode. So let's imagine we have here a copper electrode, and over here a second copper electrode. Well, if I connected this, and we have our salt bridge here, and let's just say we have copper 2 ions in solution, copper 2 nitrate or whatever. Common sense tells you that this cell here is going to give you 0 voltage. Nothing's going to happen. Electrons are not going to flow from copper to copper. Duh. But now that I've introduced to you this second way of prompting electrons to move throughout this cell, and that's by adjusting the concentrations. So even though this is still all copper and copper 2, both electrodes, let's say I make this one 0.1, and let's say I make this one, I don't know, 0.5 molar. Now because those two cells have a different concentration of copper 2, we're going to see current flow through here, and we're going to get a voltage out of this. And we call that a concentration cell. What happens in the concentration cell, if we take a look at the Nernst equation, and it doesn't matter which version of the Nernst equation you look at, because here's the important thing that happens. That E standard goes to 0 because all of that is determined by the difference in potentials of your copper and copper electrodes. So just 0. So for a concentration cell, the only thing you have to worry about is this new term that we've introduced here. And really the only thing you're worried about are, hey, what are the concentrations to help me find Q? Now if we think about it, what direction is it going to go? Well, this thing is always going to go in the direction. Let me restate that. If we look at our example here, we have a 0.1 molar and a 0.5 molar. We're going to get current to flow in ions to be converted into solids until these molarities are equal. They're going that way. They want to get to that equilibrium. So we're going to see here, this concentration needs to go down, and over here, this one needs to go up. And they'll meet in the middle somewhere. So if this one's going to go down, we need to get rid of copper 2. So here we will see a reduction. And you'll see the copper electrode here gain mass as the copper 2 is reduced to copper. And that makes the molarity of the ion go down. And then over here, you're going to get oxidation. And so it sets up as the anode and the cathode. And so once again, your oxidation is going to create ions. And since the oxidation is creating ions, this Q term tends to be anode over the cathode. And for concentration cells, that's pretty much what it'll be. It'll be the small one over the big one. It will be the low concentration over the high concentration. So I think in the Web of Science you have an example problem with a concentration cell. Just remember, it all works in Nernst equation. The only thing unique about a concentration cell is that your standard potential goes to 0, and really getting Q and using this part back here is all you have to do. But if you find yourself having some questions about it, just let me know and we can get back on and work it out.